Okay. Uh, Good morning. Um, so today, uh, we are going to continue our sections on limits. But maybe before that, I would like to just a little bit review on uh, perhaps some of your, I think, our previous feedback questions. So let me put here. Okay. From here. This and maybe this first, this log, just a review. Okay, so this is just to make sure that we are on the same page. Okay, log. Remember, in log we have, this is called the base. Okay, and how we can compute our log is basically, we can see from usually you have A or B, right? B, or let's say this is AC. We can separate this, become A plus C. Okay, so that means we have log and then we have plus. As long as we have the same base, we can multiply. We multiply the insides. So this will be log. This is 6. This is 4. 4. Or if you want to directly multiply, this will be 6, 2, 1, 6. Right? Okay. Okay, now in log, what we are looking for is the power. Okay, the power. So the right or logical question to define this log is, what power should we add for 6 to become to 16? So this is actually 6 with power of something should be to 16, and this will be our answer. Okay, so this will be equal to 3. Or we can also look at different perspectives. That is, we can take this log 6, and we know that 216 is when we have 6 with power of 3, right? It's the same thing. And we can also think that, okay, we move this to the front, and this will be 3. And we know that this part here is just 1. So again, it's the same result 3. Okay, just to let yourself reviewing a log. Okay, and a similar way, when we have, for example, log b a over c, you have multiplication, you have now defined something. Okay? Now this becomes log ba log bc. And because of this characteristic, because of this property for the log, we can use this property in many ways. Later on in our section in calculus, there will be several calculus method that can be solved through this property. Okay, either multiplication or the quotient, the dividing. Okay. Okay, that's the log. Okay, and other things is, I think we can start with this. Okay. Now to solve this, there are first you need to uh, imagine. Uh, you need to imagine you are given the functions. Okay, this is your function g. But your goal is to find the g inverse of 4. Okay, g inverse of 4. Okay. So g of x is 3 plus x plus e with power of x. So this is saying that what x that when we plug into the functions, this function here, this will result 4. Okay. I believe with some trial and error, with some simple numbers, you know that we can maybe try, because we have e, maybe we need just to power with 0. So let's just try 0. And it's true that this is 4. Okay. That means okay. Well, if you are given this type of question in the exam, the best way to do it is to show that the function and its inverse can have this property. Just to show this, and then that's okay. No need to use some other computational method to to get this x from the function. But this to show that we have this relation, then we can have some our conclusion, our result. Okay. 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 Now another feedback question that perhaps this will be introductions to what we are going to study for today is this. This is true or false. Last week in our feedback questions, the answer is true. But let me explain. Let me explain. Okay, if I give you this, okay, if I'm giving you these questions, you have a function x squared minus 9 over x minus 3. You have the second function x plus 3 is functions f equal function g. Okay, no, who are agree that it's equal. Agree, agree, agree. Okay, okay. If this is only an equation, not really a function, that's true. It's equal. But we are talking about function. What's important in a function? Domain. Okay. So remember the domain. Domain is important. Because actually, we can design functions in any way we want. Okay. We can make it piecewise defined. We can make into several functions in one big function. Okay. We can make the function, it seems like when we compute, it seems the same, but it's actually different because of this x minus 3 here. It's not defined, so the interval should be on all x except x equal 3. right? That's the domain. But here, domain is everywhere, right? Yeah, that's the difference. Okay, that's the difference. And then we bring this function, these two functions, into our limit, Okay. Now this is another perspective that we need to think. Okay. So when we have this limit as x approaching 3, and we know that in a function this 3 is not defined, but we already learned that when we have this, let's just say we have a random maybe giving there, and maybe this is a, this is L, and we know that from the limit, from the definition, intuitive definition of limit, when this is f of x, okay, the limit as x approaching a, we get the L. So the same thing when we have this x squared minus 9 over x minus 3, it's not defined on 3, but when we have the limit, they both are equal. They both will get some L. Okay? And I believe they will get around the L will be 6. Okay? Now if we would like to confirm our issue here, let's draw the curve. Let me jump into the GeoGebra. Okay. X squared minus 9. Okay. Okay. And then x plus 3. Well, x plus 3 is just the same as the same line. They both the same line, but the difference is one function here, and you will see that if you use the graphing calculator, you will not see the undefined points. But if we take some time to get in through, okay, wait a minute. Yeah, you can have, oh, this, I think they already adding this this method. So we have removable discontinuity at 3, 6. Okay, yeah. And another way we look at is the other function. So this different function, but it has the same limit. Got it? Okay, got it? Okay. And basically, this is also our introductory for today's class. When we have the limit, one thing that we can do is, first, we can directly substitute to the function inside the limit. When we have, for example, this case here, when we take this in here, we will get 0 over 0 condition. Okay, 0 over 0. So when we have limit, so if this happen, we call this indeterminate form. So what is indeterminate form? Indeterminate form means that we are not sure whether this is going to be exist or no, or it will it has a value or no. So we need to have another evaluation. Okay. So there are several evaluations. Maybe I'm giving you the diagram. Let me check my diagram. how to evaluate limit. First, direct substitutions. Second, evaluate x to a, meaning that we are going to try a and then evaluate, let's say f of a, let's say f of x, and then ask yourself that is it indeterminate form? Okay, so in diagram we can say limit as x approaching a f of x. Then we are going to evaluate the f of a, and we are going to get at least three cases, okay, three options. Either the first one, either you will get f of a will be equal to some value b over 0. Okay, so anything that has value but over 0, and we will get, in this case, we will get a vertical asymptote. Or in our case, last week we deal with the infinite limits. Okay, that limit that you have at going up or going down. Okay, that's the case. Or right here, it's infinite limit. Or you will get directly your answer, some value b. So done. Okay. Or the case on 0 over 0 situations, which we call the indeterminate forms. There are several ways to evaluate when we have this 0 over 0. First, can the functions be factorized? So try to factor it. Second, is it possible to rationalize or conjugate? The third one, is it trigonometry? Can we use trigonometry identity? Well, mostly, in our case, in our section here, these three will be the most frequent that can be applied. Okay? So either we can factorize and then we can simplify the function. We can rationalize if it is a conjugation, like square root of x minus 3, something like that, and we can just multiply with its conjugate. Or it's a trigonometry. We can use some identity, and then we can maybe simplify. Well, there is another method that actually really helpful, but there will be later another section. We call the L'Hopital rule, but let's just say we are just focusing on this three first. Or maybe there are a few methods just to approximate. Approximation. This is like some numerical method, but for our case, not really applied, okay, in our sections for limit. But there are some cases that we can have some approximations. So that's the basic. Okay. Okay, let me give you some examples, and then after some examples, we move to another sections for analysis in limit. Okay. It's called the squeeze theorem. Maybe let me add stickers. Okay, so hopefully all is at least factor, rational, trigonometry. Okay, I think we can check some examples how to get through for our limit problem. Let me move to the next page. Example, evaluate Let me start with this two. Okay, let me check. It's x squared plus x minus 6 over x minus 2. I think for the first one is you need to factor. For number one, is there any problem for factoring? Still any problem for factoring? I'm planning this for aside from quizzes that I will announce later. Maybe before the quiz start, I will have some maybe giving you some homework probably. At least I know that you know how to do it, but I think in our case here, you need to do it fast. Okay? You need to do it fast. This is really just introductory problem. So you need to familiar with the limit, and for every factorization, some algebra in calculus, it should be you need to like adapt for most of algebra operations. So you need to do all this to really quick in algebra. The limit part is just how we see the limit, and then can we direct substitute? And if we direct substitute, for example, we direct substitute here, oh, we see that it's going to be 0 over 0. Okay? That is the first observation. Okay? Because sometimes there are similar rational functions like this. When you directly substitute, you get the answer, and then you just stop until there. No need to factorize. That's some tricky questions. Because some students, because they know the math, they need some computation, they just directly compute and get the answer. Oh, this is answer we factorize, but that's wrong. You need to try to substitute first. But of course, if we substitute these questions, we get 0 over 0, which means we need to get simplified these equations. Okay, so let's simplify it here. So this will be a 0 over 0, right? So we can simplify. We can factorize. Remember, we multiply, it's getting -6, but when we plus, it's plus x. So we will have a bigger number that is positive. So we have plus 3 x minus 2. Okay. So we can simplify it, and we get that this is limit which is 5. Well, if you want to know what is happening inside this limit, okay, we could make some steps to make sure that our logic is still on the track. Okay, we are not really play with the things in our computation. So we can let's say we can have our functions is this is just to make some definitions first, okay, so that you know what's happening here. So we have this will be undefined when x equal 2. Okay, so this will be equal to x plus 3, but x is not equal to 2. Okay, this is what is really happening. So we are going to the limit of fx, which is limit which is 5. I just to show you that what is the structure. Okay? But of course, in our computation, you can directly just go here and answering 5. Okay, the second one. Let me give you some tips because I believe some of you are multiplying one by one and then making some expansions. Okay, don't do that. Don't do that. Wasting your time. Okay, limit. So we are going to x plus 1. Okay, the problem is our functions now has the square root here, right? This one. So we are going to multiply with the conjugate, which means that we are going to multiply with the square root plus. Okay. So why we need to multiply with that? Because when we have this, it's simply getting the component AB is canceling, right? So we want this happen. Okay, we want this. Okay. So that's why when we have this minus, we multiply with the plus one. So we are getting a simplified a squared minus b squared. Okay. So let's try to make that happen. So we are going to multiply. Okay. So we focus the denominator first. The square root of x plus 5, and then squared becomes x plus 5. And then 2 squared become 4. So x plus 5 minus 4, or x plus 1, right? I think I will maybe write completely so you get my idea here. So this will be x plus 5 minus 4. Okay. And just write x plus 1 here. Do not multiply. Do not multiply. Okay? Do not multiply. Here is this. Okay, cancel. Okay, so this is 4. Okay? So in under, actually, if you make it quick in under 1.5 or maybe 1 minute, you should be able to do it. Okay. So after some exercise, later I'm planning to give you some homework, just a few homework, maybe just 7 or 8 questions. Okay, 7 or 8 questions, just to make sure that you are able to make it observation on limit, and you know how to at least simplify the equation. Okay. Any questions? Any question? Okay. Okay. Remember, in calculus or in any mathematics course, the most important thing is not the formula itself, but the logic, the construction. Okay. The reasons why you are doing this. Okay? That's the most important thing. Because if you are just compute without any goal, it will be meaningless, and no, you will not get any benefit. Okay, the third one, the having the limit as theta approaching 0. So we are going to have our variable as the theta, and we have 1 minus cosine theta over 2 sine squared theta. Okay, this is also refreshing your trigonometry, perhaps in your high school, right? High school trigonometry. Yes. So perhaps this is refresh your trigonometry, because in the next chapters, trigonometry will be one of the one of the part of the techniques. Okay. Most of the techniques in calculus will also related to trigonometry. So algebra, factorizing, rationalizing, see the logarithm, and then trigonometry. There is, well, I could say like a main course in the dishes. Okay, Now trigonometry. Okay, let me just give you some basic trigonometry that probably we need to use more and more over the time. So first thing is we have this. Okay, I hope everyone agree and remember the sine squared plus cosine squared equal 1, right? So this is tips. Okay, tips. The first one is this. The second one, let's just multiply with the 1 over cosine squared. This will be tangent. Okay, the second one is that. The other formulations from the trigonometry that might be helpful is the double angle. Okay, the double angle. Okay, another one is okay. I think these four. The last one can be three formulations. Depends on where we are going, but they are the same. So I believe this is frequently will appear, okay, in the future. Okay, in the future. So sine squared plus cos squared equal 1. Tangent squared plus 1 equals secant squared. And remember, do not memorizing without any understanding behind this problem. Okay? Or do not blindly memorize all of this. Okay? This. Oh, wait, this. Yeah. But perhaps how to get these formulations, I will maybe that will be on the basic of math. But for calculus, we don't really have time to get through that, all of that. Okay, now from our question, we can look up this limit. Okay? And we know that we have sine squared. We have sine squared. And you will see that at the numerator, we have 1 minus cosine. So perhaps we can correlate this numerator and denominator. Maybe we can cancel something out, right? So let's try to make this out. Let me write with the brackets so you see the where it is going. Okay? So sine squared, I will change this sine squared becomes 1 minus, or maybe let me put down here. This is 2, 1 minus cos squared theta. Remember, this is 1 minus cos squared. Okay. Now, perhaps we can factorize. We can factorize this. And this will be Oh, before that, I forgot to mention. We need to check first, okay? We need to check first. Check this. Cos 0 is 1, so 1 minus 1 is 0. Check here, sine 0 is 0, so it's 0. So that's okay, 0 is 0. It's indeterminate forms, and we need to simplify, okay? Okay, now we try 0 inside. It's 1 plus 1 is 2. 2 by 2 is 1 over. Maybe let me make it bigger. Okay, any questions? Any questions? Okay. I hope it can refresh your memory on trigonometry. Okay. Let me continue a little bit. Okay. This is example. Okay, example. Okay. Another note that I want to perhaps emphasize is another example, but this is let's say limit. So we have absolute value of x. So if you can quickly imagine how it looks like in your mind, you will definitely get directly, oh, this should be some number. But what graph do you draw? Okay. First, we need to remember how the absolute values will operate. Okay. So absolute values, we can have this is positive and negative, right? But when does it positive? When? We need to define the interval. This should be, the interval should be x greater or equal 0, and this will be negative with x less 0. Well, sometimes this also true. It doesn't really make that difference, but the default way is the left one, greater or equal 0. But if you switch both of them, it should be okay. Not really a problem. This is saying that the interval will be all true except at x equals 0. There will be something there. Okay. Because if we make both of them equal like this, in mathematics, this a little bit weird. Okay, a little bit weird. So we need to just choose just one of them. Okay. Let me erase this part. So we can make our graphs. I think we can draw easily. Okay. So this will be y equal absolute value of x. So there will be component here that is not really like a curvy, but it's just a sharp point Okay, we call it sharp point. Okay, now in terms of limit, we can analyze from each side. Okay, so let's say we try to analyze from the right. So from the right, then this will be the interval. Okay, this interval, positive one. So we will have just x. Okay, and of course this will be 0. And then we can analyze from the left. And now this will be negative x, right? But since it's just 0, negative, it doesn't really matter. Okay, so it's also 0. And then remember, the property of limit, okay, we can say the limit exists if limit from the left is the same with the limit from the right. Okay? So we can say it exists. So conclusion, limit from the right is equal limit from the left is equal so that's how we analyze our limit. Okay. So first, if the limit easy to draw, you can draw. Okay. But if not, then maybe we can try to make some interval. Okay. We try to make some interval if we have some domain, okay, for certain function, and then we try both sides. We try from the left, we try from the right, whether it's the same or not. Especially the left limit or right limit uh, will be useful if we have piecewise defined function, and you have the interval, and you can try the interval. Okay, okay, I think we can. Hey, we can take a break. We can take a break for a while. Okay, let's continue. Let me give you another limit as x approaching 0. Now we have the denominator x, okay, in this rational function. We have absolute value. We have done before the absolute value, but we now have the over x in the function. But now we could just check the x approaching 0, and when we check the possibility in our limit, it seems that it's 0 over 0. But for our convenience, I think we could analyze through the how this function will look like in a graph. So the best way to deal with this type of question is, because we know that the absolute value of x, it can be positive or negative when we have this, right? So when we add the over x, since the domain itself, so we are moving out the x equals 0. So this will be going to be x, let's say x over x. Let me just write x over x first, which is the positive, and then this will be equal to negative x over x when x is negative, okay? Now if we deal with the limit, then we could start with limit, let's say approaching 0 from the right, okay? Approaching 0 from the right. Let me write completely the questions, and this will be going to be x over x, or we could just simply say this is going to be 1. And if we have the left limit, the left hand limit, this will be negative x over x, which is negative 1. And what is our conclusion? The limit, because it has differences in the left right limit, then the limit doesn't exist. Okay? The limit doesn't exist. So we could say, since limit from the right is not equal limit on the left, then limit let me just write the NE, it doesn't exist. And of course, you can also imagine what it looks like. Uh, this is the graph. So you see that when we approaching 0, both sides is not equaling the same value. When we approaching from the right, it's going to be 1. When we go to from the left, it's going to be -1. So we say it doesn't exist. There is some interesting functions that perhaps you could try to find out. But let me just try it and um, give you some thoughts on that function. Okay. So consider a function of x is equal to. So what this bracket means? This bracket means that this is the largest integer. So how do we deal with this? Okay. How do we deal and how to operate this? Okay. So for example, let's try some x that has decimals. Okay, that has decimals. Or let's try some x. Okay. So let's try x equal 2. X equal 2. So f2 is just 2, and this is just 2. Okay. If we have f say 4.8, or maybe let's make it similar to 2.8. This will also give the largest integer on this part, that is 2. Okay, and we have, let's say, 3, or 3. This will be give the results same 3. But what if we have pi? Pi, if you remember, is 3 point something, 3.14 decimals. So we take the largest integer, and this is 3. Okay. Now, if we graph, the interesting point on this integer, on the largest integer, is that when we graph all these results, this is what it looks like. So if we took some decimals, around this 0, 1, or 1, 2, 2, 3, they will, well, we could start from the last one. So let's start from 0. We get 0, and then every time we move to 1, it's still 0. Okay, it's still 0 up until 1, but when it's 1, we move out to this point, right? And then 1.1, 1.2 is still the same. We take the largest integer on that up until nearby 2. But when we have 2, we get another one here, and it will goes around all the way. And the same thing happens when we have the negative part. Okay, so it's kind of make some constructions that is in each unit. If we divide the unit by 1 unit, we will have like a small line that is, it seems like they have a pattern, but they are not connected. And if we take some limit around this part, we will not have this limit to be exist. So for example, if we take the limit as x approaching 2, well, if we look on this 2 here, go from here, from the left, go from the right, it doesn't exist. So this will be doesn't exist also. Okay. So this integer, it will be exist if the limit we approach is in between this 1 unit. Okay. For example, 2.5, 2.6, we will get the limit. Okay, we will get the limit. So this is called the largest integer functions. I think it's better to understand these functions through the picture. Through the picture. So the left one include and go to the right, and then having a whole, and then move to the 1 unit up, and go 1 unit right, and go 1 unit up, 1 unit right, and so forth and so on. That's it. Oh yeah. Is it shaky? It's shaky, right? And so I think that's it's from the days ago, a few days ago, right? Yeah. Oh yeah, yeah, yeah. Yeah, it's called the when you have an earthquake, there will be some because the earthquake is actually they want to stabilize the the Taiwan is came from two you say what kind of two plates, right? Two plates, and they want to stabilize, so they want to release the energy through earthquake. So that will be dangerous if if one in 1 year if we don't have any earthquake, that will be dangerous. The next year probably bigger, will be more more terrible. Okay, so if we have like small, it will be okay. It will be okay. It will be stable. Okay. 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 Now the next thing is my plan is to give you the squeeze theorem and the squeeze theorem. Now let me move to the next page. Okay. Okay, let's say we have this is just a random function, the green, red, and blue HGF. Okay. And we see from this general overview, okay, let's say we are going to take the interval from 0 to the positive interval. From that point, we see that the function, okay, will take the function of x. This will be less equal g less equal h. Okay, because they are equal when they are in x equal a. So here they have the same amount of value, but in general we see that we get this inequality. Okay, so f less equal g less equal h. The theorem said that so if this happened, and let's say limit x equal a, let's just say f of x. If we take this as L, okay, as L, and and limit Sx approaching a for h also L, okay, then limit as x approaching a of g of x will be also L. Okay, this theorem is called the squeeze theorem. Okay, let me write the name. This is called the squeeze theorem. Or sometimes you call pinch theorem, pinching theorem. This theorem is really useful if we have some functions that perhaps we are not really well, we cannot simplify it easily, okay? But we for sure know some functions, some other functions, okay, for that value. For example, let me just give you example. Okay, let me just give you example. So if we have a functions, let me just give example directly. Limit x approaching 0, x squared sine 1 over x. Now, of course, if we look at this will be very, very terrible, right? If we try to plug in 0, we don't really know what happens, right? So the best way to look at this is look at this trigonometric sign. Okay, look at sine. Sine 1 over x. Every time you use this trigonometry, either cosine or sine, they will have the maximum value of +1 and the minimum -1. Always, right? Always. Okay. So we hear that this is going to be having the -1 and 1, right? Okay. And if we for sure want to multiply with x squared, okay, we can have this correlation and inequality. Okay. So we can use our squeeze theorem. So let's say this is F, this is G, and this is H. And of course, the left and right, we can know for sure that when we have the limit, it will equal to 0. So because of that, then our squeeze theorem says that it will also equal to 0. Okay? We can prove this with our visuals later. So we can say that because limit, or maybe limit as x approach 0, -x squared is 0, and limit is 0, then by squeeze theorem, limit okay, and it can happen with many cases. Okay? As long as you can prove that you have this at least 3 functions, the last functions and the left function and the right function, you know for sure the value, then you can figure out the middle one. Okay, that's the squeeze theorem. But what is really going on with this function? If you want to like confirm our theorem here with our graphs, I think we can take the graphs. Okay, let's delete. One over x. Okay. Okay, we need to make it a little bit closer there. And then try here, and then add another one, negative x squared. Okay, I think, well, you see, this is our functions. The x squared sine 1 over x, when it's reached 0, it's getting some oscillations and getting the gap getting closer, and becomes going to 0. But we need to make sure that our squeeze theorem is works. So we need to take this x squared and negative x squared. And it's perfectly aligned with our theorem. So this x squared is on the top, and the middle is our function that we want to determine. The bottom one is negative x squared, right? Okay. And the function in the middle is perfectly in the middle, okay, in between x squared and negative x squared, because we know that the sign is always have maximum 1 and negative 1. So our statements are true. Okay. Well, let's take screenshot and put in our notes. And let's say this is x squared, and this is negative x squared, and the middle part is okay. Within this squeeze theorem, I would like to try my best to prove. Is this okay? So try to prove that limit. Um, let's use theta sine theta over theta is 1. Okay. Okay. Now, before we use the squeeze theorem, we need to define this theta in geometry. So we start with this. Let's say the circle. Start with the circle, just a regular circle. Oh, sorry. And then start to define the radius. And then make out a small sector, like when you are cutting pizza, right? We call it sector. Okay, the small part is we call sector, and we define the angle is here. Okay, and we have a radius here. Let's say the radius is just a constant. And to make it easy, maybe we could just take radius equal 1, okay, to make it easy. Imagine that's the assumption. Okay, and then the sector, let's put the straight line the height, and also another line that's connecting this and becomes triangle. Okay. And then we can have another line going outside there, maybe here, and then connecting this line here. Let me put the other color. Okay. This is all connected to this part. Okay. So you have several triangles. Okay. Let's pick some points to define which triangle we are going to observe. Okay. So I say this is O, A, this is D, B, C, and let's put another one here, the small part here, and saying that this is E. Okay, according to our triangle here, we take the sine theta is equal with the triangle inside the circle, that this is the distance of BC divided by the hypotenuse, the 1, or we could say that this is just the distance from BC. Okay, that's sine theta. Okay, and then consider the arc AB. What's the arc? The arc is the curvy part on the sector. So if we take for circle, okay. Now this is the arc. This is we call the arc. Okay. So arc AB means the sector on the from point A to B. This is precisely, if this is a theta, then theta over 2 pi multiplied by the circumference of the circle. Or we could say that this will be theta r. But since r is equal 1, we make it into a constant 1. We could just say that this is theta. Okay? Okay, so we have sine theta, we have the arc AB. And then we look on another part from the triangle. We observe the big triangle OAD. Okay, observe OAD. If we take a tangent, okay, a tangent. So we take a tangent, maybe right, maybe here, okay, to give you clear image. So let's say the tangent theta is AD divided by OA, right? The R, or it's just AD. Okay, so we have a sine theta, arc AB, and tangent theta. Okay, let me copy this and make another circle on the below. Okay, now let me paste this and let me write something. Consider the arc AB, and if you see from the picture and proof in our geometry, the arc AB will be less than if we have AE plus AE and EB. Of course, the arc AB will be less. Okay, if you see the picture, so arc AB is this one, and AEEB is, of course, it's having more length. Okay, if we compare to the arc AB, and also the arc AB is also less. Of course, it will be less than AE and ED. Okay. Which means that this is the AD, right? AE and ED. Okay. And from what we have, arc AB is a theta. This will be less than tangent theta. Okay. Or we could say that the theta is less than sine theta over cos theta. Okay, and then we include our AB. Okay, so we have AB, okay, so we have AB. So let's say AB, and we have the arc. Okay, of course, AB is less than arc. Okay, so AB is less than arc AB, which means the AB is our sine. Wait, AB. BC, AB. Okay, I think we can make sure that if we have this, if we take the let me write here. Forgot to mention this is theta. This is OBCA. Okay, sine is BC. Okay. Okay, and then from here we get sine theta less uh, sine theta over cos theta. Well, this is maybe let me go through. we could say that this will be, okay, I think that will be okay, right? Yeah. So we could say that this theta is in between sine theta and tangent. And let's multiply with okay, multiply with the cos theta sine theta. Cos theta sine theta. So this will be cos. This will be cos theta cos theta sine theta. Or maybe not really good. The best way is to reciprocate. Okay, so reciprocate becomes 1 over theta. This becomes that. This becomes that. And then this becomes cos theta plus sine theta over theta less than 1. Or maybe to make it clear, maybe we multiply with 1 over sine. This will be 1 theta sine theta. This will be 1 over cos theta, which means we reciprocate, this become this. And we move on or exchange the cos theta and 1. So we move here, we move here. Okay, well, I will explain later. And then from this part, we take the limit. And since y is x, sorry, it should be theta. This is 1, and this is also 1. Then by squeeze theorem, how many times do we have left? Okay. Limit is also 1. Okay. There will be another approach. Okay. So this part, okay, this part is I'm approaching the geometry through the length. Okay, the length of some parts in the triangle and the circle. However, there is another way to look at, which is through the area, and I think the area will be very very clear the differences. Okay. Okay, perhaps there will be some confusing part on this this inequality, but let me just give you an explanation here. That this is the first inequality we get. Okay, I'm dividing all by sine. Okay, divide by sine, and go here first, and it's 1 less theta over sine and less than 1 over cos. What I did is I reciprocate. Okay, so from x to 1 over x. Okay, so from this theta over sine theta, I'm going for this sine theta over theta, which implies that we need to change the left and right. So we move out. Okay. Or if you would like to see from this part, this is also okay. And then go here. Okay. Oh, sine theta over theta, sorry. Okay, and then we can put in our squeeze theorem. Okay. Okay, I will explain more about this perhaps tomorrow. Okay, because I think we don't really have much time. So the idea behind this is basically to prove through the geometrical length, okay, inside the triangle and circle we have. Okay? So this is the best way to check the using the unit circle or the right triangle, inside the circle. And we fix the radius into 1. Well, you can use radius as r. Eventually, it doesn't really matter in the proving part. So I will make this simple, taking r equal 1. Okay. And then what we are going to do is we take the sine theta from this part. So we make out our sine theta so that when we have in the last part is we have its relations with the theta, which we get from the arc. Okay, we get from the arc, okay? From the arc length of the circle. Okay, and then we correlate that part, and we need to have another comparison, which is we get from the big triangle AD. That is the tangent. Okay? So we have at least 3 functions from there: sine, theta, and tangent. And we need to simplify the inequality to prove that we can make out our squeeze theorem from this sine, theta, and tangent. Okay, that's the idea. Okay? That's the idea. The rest is to make sure that your geometrical proof is correct, and then we can make sure that all this are all true. Okay? There is one way, another from this, using the area. I think it's much more, I would say, much easier to see, because this part is we need to make sure the geometrical length is true, and that is a little bit difficult. So that's why we have all these lines here, just to prove that that is really less than the other part. Okay, just to prove that, okay? The geometrical length. Okay, I think I will stop until here. We will continue a little bit on this tomorrow. We will see the comparison with the area. Okay? This is the length, and we will see the area, and we can still use the squeeze theorem. Okay, I would like to start the feedback questions as usual. Okay, I hope you don't mind. Uh, okay, start. Oh yeah. Okay. Is it okay now? I hope the time is enough. I think 3 questions, but um, like not really that long question. Okay, let's start. Okay, please use your student ID. Okay, let's start. 3, 2, 1. Okay, this is, I think I haven't really explained, but this will be on. I have explained a little, but let me just emphasize this tomorrow. Okay? I think I explained a little on limit law. Limit law. Okay. You can check your notes on limit laws if you remember. And careful on the sentence, okay? Sometimes true or false is confusing. Okay. Okay, it's true. It doesn't exist because of the denominator is 0. Okay. Okay, if you can change your name to your student ID, please do that. Okay, so I can make sure you're great. Okay, let's go. Number 2. Okay, get ready. Okay, start. Sorry if the picture a little bit small. I think the time is too fast. Is it too fast? Yeah, should be 2 minutes, please. Yeah, sorry. But I think if you can optimize, I think should be okay. I think for some smartphone, it's too small in your screen. Is it right? Too small? Okay, so sorry if the time is really fast. Okay, I forgot to add more time in this question. Yeah, but I think okay. I think good, very good, nice. I think still okay, still okay. If you get wrong in any feedback quiz time, still okay. That's it's for your exercise. Okay. All right, last question. Get ready. I also forget the question, which. Oh yeah. Okay, compute. Giving you 1 minute 50 seconds. I think the calculation should be not too complicated. I think you can do on your mind really fast. Remember the a squared, b squared, and I think you can cancel that out. Okay, 15. Okay. 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 Who's the the first one? Okay. Good. Okay. Okay. As usual, write your student ID if you finish, so you can go. Okay, if you finish, then that will be the end of my lecture. See you tomorrow. Okay, we will continue. Have a nice day. Okay. See you. Yeah. See you. See you.